And if you got a silly thing you can say to yourself in your head, that's going to make it even more likely that you'll be able to do the sequence right. So, all right. Time for Chapter 3, Molecules, Compounds, and Chemical Equations. Chapter 2 was just about atoms and elements. So we were dealing with elements, and we were dealing with the individual atoms that made them up. Now in Chapter 3, we are combining atoms of different elements together to make compounds. And it turns out that it's chemical bonding that makes the true difference between compounds and mixtures. Because true, compounds are a combination of different kinds of atoms altogether. That's technically, I suppose, what a mixture is. But the difference is that in a compound, those different types of atoms are bonded together in specific amounts, specific ratios, specific locations even, where a mixture is just kind of whatever, just sort of all thrown together. But chemical bonding is really the true difference. Okay? There has to be chemical bonding in order for there to be actual compounds. So this inside of this balloon here, this is a mixture. It's a mixture of hydrogen molecules. Okay? That is an H2 molecule. It's a molecule because there are two H atoms, right? We would usually draw it like that. Two H atoms that are bonded together, okay, to make that molecule. This is an O2 molecule. Okay, two oxygens bonded together. But this whole thing overall is a mixture because the hydrogens and the oxygens are not bonded. We could very easily add more hydrogen to that, or we could add more oxygen to that. Okay? It has a variable composition because we could very easily add any of the ingredients to it without really changing the overall makeup, just the amounts. Okay? Now, there's a main difference here between this water, which is a compound, because water is made out of H2O molecules. Okay? H2O molecules look like this, where it's specifically two hydrogens attached to a single oxygen. And you'll notice every single one of those looks exactly like that. So this compound has only one type of matter present, essentially. It's the only thing that's in there are these H2O molecules. We could not change this composition and still call it pure water. Where we could change this composition and we'd still be able to call it a mixture of hydrogen and oxygen together. Okay? So let's talk about two of the most important types of bonding that allow atoms to combine to form compounds. Okay? Ionic bonding and covalent bonding are the two main forms of bonding, and it's going to be very important that you know the difference between them and when a bond is ionic versus when a bond is covalent. That's going to be that's one of the key ideas of introductory chemistry, essentially. Okay? If you've taken high school chemistry, or if you've taken an introductory chemistry class, okay? The difference between covalent and ionic bonding is one of those very important things. So let's talk about how ionic bonding happens. That's the attraction of oppositely charged ions, and we have that when we have a metal and a nonmetal. We saw last time that metals form cations, for instance, like sodium. Sodium loses one electron to form Na+. That's our cation. And there's that electron. Okay. What do nonmetals like chlorine do to form an ion? They gain electrons. Chlorine gains one electron. That's a gain. There's our chloride anion, Cl minus. What we didn't tell you last time is that this electron over here doesn't just fly away. Okay? This electron is actually the same as that electron right there, if the sodium and the chlorine are in the same container as each other. So another way of drawing this might be something like this. If I had a sodium, here's that one extra electron that it has and it kind of doesn't want. Okay? And chlorine, we'll talk about valence electrons later on, but it has 7 electrons in its outermost layer, in its outermost shell. And it turns out that the sodium gives that electron away and the chlorine takes it. Okay? It's essentially an electron transfer where we end up with Na plus and Cl. We can draw those electrons in there. Here's the new one that it just got, and now that chlorine has a minus charge. Okay. But that's just how the ions form. Okay? The ions are the positive or the negative charged particles. That's how the ions formed. Okay? The ionic bond is the attraction. Okay? So why would those newly formed ions become attracted to each other? Because they have opposite charges. Okay? Anything here, let's just make a, I always struggle with the clearest way to draw this. Okay? Here. I'm just going to do it like this. Just going to show the charge. Okay? Attraction of oppositely charged ions. That's the ionic bond. That happens. Okay? So after there's an electron transfer, that makes oppositely charged particles, because one has lost an electron, one has gained an electron. Now, because they're oppositely charged, those two newly formed ions stick to each other. Okay? They literally are pulled close to each other because of their opposite charges. So take a look at this little picture here. The microscopic view of some sodium chloride is oppositely charged ions, plus, minus, plus, minus, all stacked up like that. Okay? Alternating, stacked ions. Because it turns out that this plus isn't only attracted to that minus. This plus is attracted to any minuses that are nearby. Okay? And assuming it's not just a single pair of atoms we have, what we're actually going to end up with is a positive ion, like that one, that has negatives on all sides of it. And then a negative ion with positives on all sides of it, three-dimensionally. Okay? In sodium chloride, when it's just a 1-to-1 ratio like that, there are going to be two opposite ions above and below, left and right, and front and back of that. So any one of those ions will actually be touching 6 of the opposite charged ions, but each of those will be touching 6 of their opposite charged ions, okay, all around them. So overall, that makes a 1-to-1 ratio in this case, right? NaCl from its formula, 1-to-1 ratio. We'll talk about why that is in a second. Okay? But it's very important that you understand, and we're going to be talking about this an awful lot, that when we have an ionic compound, when we've got a metal and a nonmetal, they had to do an electron transfer, and then those ions are attracted. Okay? And it also has to be clear, that little picture of those alternating stacked ions for you. Because there's no direction to ionic charge, they're going to be attracted to their opposite ion sort of on all sides. So an ionic compound has big stacks, okay, rows and columns. This whole salt crystal will be made up of these stacked ions going all the way to all the edges. Okay? It's very important because we're going to compare that with a covalent bond. A covalent bond does not come from an electron transfer. It comes from sharing of electrons. Okay? It ends up with a pair with two electrons that are shared between a pair of atoms. This is what happens when we have two nonmetals that need to be bonded. Okay? Like the simplest example is hydrogen, which has just one electron, and another hydrogen atom. If they get close enough together, they can share that pair of electrons between them. And we actually draw that as a line. So whenever we see atoms connected by a line, that line is a covalent bond that contains two shared electrons. Okay? There's a pair of electrons in there. It does it this way because if they're both nonmetals, they both kind of want electrons. We learned before that metals have excess electrons they want to get rid of, but nonmetals want electrons. So if two nonmetals are bonding to each other, one of them is not going to give up one of its electrons. They both want electrons. So the only way that they can bond is if they share some of their electrons. And we're going to get more information that sort of fills that picture in as we go. Okay? But that's very important. And the main consequence of this is because this type of bonding is directional. Okay? It doesn't just happen, it's just not a force field in all directions. Okay? This has to happen specifically in one direction. And the number of covalent bonds is restricted. Okay? It depends on how many electrons there are to share. So what that means is here we form molecules. Okay? Groups. Covalently bonded atoms. Okay? So, you will get really funny looks from people that have taken chemistry if you talk about sodium chloride molecules. Why is that? Why is there no such thing as a sodium chloride molecule? Yeah, sodium chloride is ionic. It exists as stacks of alternating ions, okay, going all the way up. Okay? There is no individual little grouping there. It's just all stacks. They're all alternating. Okay? Whereas a compound made with covalent bonds, that happens in a very particular direction in a particular way. Okay? The atoms connect together like little Legos or something like that in very specific ways. So the hydrogen molecule, okay, it exists as two H's like that. Here's a water molecule. Okay? You can already tell something about oxygen's behavior because oxygen forms those two covalent bonds, okay, to each of the hydrogens there. But a totally different looking compound. Okay? They're both compounds because they have a certain ratio of elements, and there's chemical bonding that defines them. But it's a totally different idea. Here the chemical bonding is within those molecules, but each of those molecules are pretty much independent of the other molecules. Okay? Whereas down here, the whole thing is all together, plus, minus, plus, minus, plus, minus, plus, minus, plus, minus. Okay? Does that make sense? So I'm perpetually slightly disturbed by the fact that there tends to be a subset of students that finish general chemistry without having that very basic, very general idea about the difference between a molecular compound and an ionic compound at that level. Yeah, go ahead.
Does the ionic bond have anything to do with how easy it is to dissolve NaCl into water?
Yes. Yes, quite a bit. I don't know if I can elaborate much more than that right now. If those of you that are going on to take second semester chemistry, you're going to talk very specifically about the strength of these forces. So when you're dissolving sodium chloride, you're replacing those ionic bonds with attractions of water molecules, okay, going around them. Whereas there's not quite as much of a distinction for that within those compounds. So, it's relatively easy to break up some ionic compounds by surrounding them with water molecules. It's very, very difficult to break up molecules themselves. So it takes a chemical reaction, combustion reaction, or something like that to actually tear molecules themselves apart. However, as we'll learn, it's very easy to separate one molecule from its neighbor. Okay? That's what happens when water evaporates or boils. Liquid water has molecules all next to each other. Gaseous water has molecules separated way far apart from each other. Okay? So totally simple to evaporate or boil a molecular substance. Much harder to evaporate or boil an ionic substance, right? Because we have to break those very strong ionic bonds that are pushed right up next to each other. So some previews for things to come there. But right now, boy, you would be in a great place if you can picture in your head that a molecular substance and an ionic substance have totally different ways that they're sort of laid out. Okay? And how would you tell just from the formula whether something is molecular or ionic? Just H2O versus NaCl. How do you tell from those formulas which one is which? Yep, it's all about metals and nonmetals. It's all about the periodic table. Okay? If we've got a metal and a nonmetal, we know that the metal had to become plus, the nonmetal had to become minus, so there'll be opposite ions all stacked up in an ionic compound. Okay? If they're both nonmetals, like H2O, here's a periodic table somewhere. Okay, here's the nonmetals, right? If we ignore the metalloids, I think we said this, maybe we didn't. What's the other nonmetal on the periodic table that we've just been talking about? Right, these are all nonmetals here, but there's one nonmetal that's not in this part. Yeah, hydrogen is a nonmetal. If you missed that detail at one point, you were probably very confused a few minutes ago. But yes, hydrogen is a nonmetal. Hydrogen, we talked about how hydrogen is totally different from pretty much everything else in that first column, okay, in about every way. So some periodic tables have hydrogen detached from that first column, even a little bit. Okay? But yeah, hydrogen is a nonmetal. Okay? When we have pure hydrogen, it is a gas, okay? Although it's made up of H2. Okay? Diatomic molecules. All right, so